Hi, welcome to the screencast for topic 10.4. In 10.4, it's all about alcohols. So alcohols are very similar to alkanes, but now you have an OH group or a hydroxy group substituted in place of one of the hydrogens. And this functional group can be on the end, or it could also be on a branch, or it could be on one of the middle carbons of the straight chain. So the OH group, being similar to water with the hydrogen bond, becomes a very polar group. At least around that OH group, it's very polar. So alcohols are more soluble in water, but of course it depends on how long or how big an alcohol you have. The bigger the alcohol, the less that polarity comes into play. So smaller alcohols are going to be the most soluble in water. It's also going to make them less volatile with higher boiling points and more dense, having that polar bond on there. They're going to burn with oxygen to produce water and carbon dioxide while releasing a lot of energy. So the combustion equation for an alcohol looks very much like it does for an alkane. If we just go with methane here, you'd have CH3OH plus O2, and your products would be the same, CH2 and H2O, and then you just have to go ahead and balance that. And you can see a 2 in front of the O2 and the H2O takes care of balancing that. Other things you should be aware of with alcohols, they burn cleaner than alkanes, which is why ethanol has become a big deal with gas, especially in Minnesota where we have a lot of corn. Ethanol is added to gas. It does decrease your gas mileage, but it burns much cleaner, so you pay less for that gas, and it's pretty much, a break-even deal that you pay less but get less gas mileage. So in the end, it's not costing you any more, but you're doing something better for the environment. As the size of an alcohol increases, as I mentioned, so does the amount of heat released, since it'll form more CO2 molecules. And the reason that's important is CO2 molecules, remember, have two double bonded oxygen, and so that takes a lot of energy to form those bonds. And again, if you think about your enthalpy diagram, since this is exothermic, this is where the bond making is. So if that bond making takes a lot of energy, which it will for these two double bonds, that means a lot of energy is being released in the process. This slide, I've just got some things on there that just are good things for you to know in general about alcohol, but not anything that you're necessarily going to be tested on. Methanol can be burned directly just like ethanol is, and this is an area of exploration because this would allow us to have vehicles running on natural gas, or this is what they've used in fuel cells to produce the hydrogen for hydrogen operated cars. So just something interesting as we look at alternatives. Ethanol is also the alcohol that we can safely consume, or at least in moderation it's considered safe. But when you hear about alcoholic drinks, ethanol is the alcohol involved. Most other alcohols are toxic to us or cause a lot of damage. But because ethanol alcohol is used so much in industry, it's used as a base for a lot of things, especially for industrial cleaners and disinfectants. When they do that to keep people from buying Lysol as a cheap drink, which, as sad as it sounds, people do this, alcoholics will tend to drink anything they can, and so that would be a cheap drink for them. What they have to do, and I guess also kids could drink it too as part of the reason for it, but it's required that it be denatured. And what denatured means is that you change its natural compound into something that makes it unfit for human consumption. So a toxin is added to it. So even though Lysol and other cleaners are made with ethanol alcohol, they deliberately change it to make it unsafe for human consumption. And again, so that people who shouldn't have it aren't buying it for that purpose. Okay, looking at the oxidation of alcohols, when you burn an alcohol, like with the equation I just showed you, if you have methanol and you combust it with oxygen, that's considered the complete combustion. So CH3OH plus 2O2 and then our products were 2H2O and CO2. So if all the alcohol, all the carbons get converted to carbon dioxide, that's complete combustion. But Oxidizing agents are often used to make sure only the carbon atom attached to the functional group, to the hydroxy group, gets oxidized, because that allows us to produce aldehydes, carboxylic acid, and ketones. And the agent that's typically used is what's called acidified potassium dichromate. And if you take a look at that, you've got, oops, sorry about that, I'm just trying to clear my ink. If you take a look at that, potassium dichromate would have chromium 6 plus, and when it reduces, it becomes chromium 3 plus. And what's also handy about it is a color change accompanies it. It goes from being an orange color to a green color, so you can tell when the reduction is complete for your acidified potassium dichromate. And so this is commonly used with alcohols, like I said, to produce either aldehydes, carboxylic acids, or ketones. Now, what you get produced depends on whether you have what's called a primary, secondary, or tertiary carbon that OH group is attached to. And you maybe remember from back in the earlier sections of Chapter 10, a primary carbon has one other carbon attached to it, a secondary has 2 other carbons, a tertiary has 3 other carbons. So on the following slides, I'm going to look at each of these types of alcohols, or carbons more technically, and what happens as you add oxygen or oxidize those. And for each of these, keep in mind that we would be oxidizing them in the presence of this this oxidizing agent, or this potassium dichromate being reduced. So first one we'll look at is oxidation of a primary alcohol. And so I've got the chemical formula here, and I'm actually going to sketch it out too to show you a little more visually what's happening. But as it says, oxygen and heat will remove 2 hydrogen, or that would form H2, from the CH2OH and leave behind an aldehyde. So if we look at how that happens, I've got my carbon with 3 hydrogens. I've got my next carbon, and on this carbon, I have the functional group. So I'm trying to oxidize just this carbon group. This is the part I'm interested in. This carbon group, the CH3 group, isn't going to be affected. So when I remove hydrogen from this, I'm going to remove this hydrogen and then one of the single hydrogens. And when I do that, H2 is going to escape, which they don't typically show on here, but should be aware that H2 is produced. It has to go somewhere. And so then if we look at this, what we have left is a double bonded oxygen. There's still 1 hydrogen left, and then my methyl group is unchanged over here. So I have gone from methanol to methanol. So that is an aldehyde. So that is the first thing that happens when you oxidize a primary alcohol. Now, it's possible you can get that to further react and become an organic or carboxylic acid. And to do that, it's a little bit tricky. You have to use something called a reflux condenser, and I've got a picture of this on the next page. But by the time you heat this up, remember, alcohols are pretty volatile. They become a gas very easily. So as you start heating this, you need heat and oxygen for this to take place. That primary alcohol is going to become a gas, and your aldehyde is also going to be a gas. And that gas is going to escape unless you collect it. If you collect it over into another container, it will liquefy into your aldehyde, and that's great. You can use that aldehyde, or you can force the vapor to stay in that same container, and that's what they call reflux. Reflux is when something goes up and down. If you hear people with acid reflux, they have stomach acid going up and down their esophagus. Well, this is basically the same thing. You've got your boiling container, and then you've got a long tube on top of it like your esophagus for it to reflux or go up and down. And so as the vapor rises up in that tube, it cools down, liquefies, and drops back down into your beaker. So in your reaction vessel, you have primary alcohol in there, but you also have aldehyde. So that's why we have the second reaction then. This aldehyde now gets exposed to oxygen. And this time, being exposed to oxygen, instead of removing hydrogen, we're just going to add oxygen. So instead of taking 2 hydrogen off and forming H2, we're simply going to add oxygen back in, and the place it's going to add back in is, so I've got oxygen here, and now an oxygen is going to insert itself back in here. So over here, we remove 2 of the hydrogen, which escape as H2, leaving behind an aldehyde group. This time, we simply add oxygen back in right here, and now it forms a new functional group, a COOH group, or a carboxylic acid. So primary carbons can produce 2 different organic compounds, and commonly are used for that. So as I scroll down, I just kind of summarized those same ideas on the bottom here. And if we go on to the next slide, here's a picture of what's going on. So this is the apparatus. In this first one, you can see that the alcohol, this is your alcohol in here. And again, it's a primary alcohol. And the vapor is allowed to travel over here and cool down. So this would be an aldehyde being produced and collected. But over here, you've got alcohol in there, but now the aldehyde, when it rises up, it recondenses and comes down, and so you form an alcohol and an aldehyde. So ultimately, you're also going to be producing some carboxylic acid, so you'd have both products showing up in the second setup. So moving on to secondary alcohols. Secondary alcohols basically undergo the same process, but we come up with a slightly different product because a secondary alcohol is a carbon between 2 other carbons. So ethanol would be my smallest alcohol that could be a secondary alcohol. And if I sketch the picture here, I have my CH3 group. I have my carbon with the alcohol group attached, and then another hydrogen. And I have a CH3 group on the end. So if I go ahead and add oxygen to this, I'm going to see basically the same process as we had with the primary alcohol. I'm going to have this hydrogen, and now there is only 1 hydrogen to take off. But I'm going to have hydrogen removed, and when I look at what's left then, the oxygen remains behind, but now it's sandwiched between 2 carbon groups or 2 R groups. So instead of forming an aldehyde, I formed a ketone. So really it's the same process, but the location of the oxygen puts it into a different family. And then the last possibility is oxidizing a tertiary alcohol. And tertiary alcohols, because it's surrounded by 3 carbons, it would require a lot more energy to do this because that COH group is going to be hidden for one thing. It's going to be a much harder location to get to, and you'd have to actually break the carbon skeleton. You're actually going to affect the carbon skeleton to do this because there is only 1 hydrogen with that OH group, so the other hydrogen is going to have to come from one of the other CH3 groups, which is going to really change things up. So the bottom line is tertiary alcohols do not oxidize as a general rule. You could force it to happen, but it just isn't worth it. There's not a reason to do it. Just a reminder again that with the primary and secondary alcohols, though, part of them oxidizing is something else has to be reduced, and it's the potassium dichromate being reduced from +6 to +3 with that color change from orange to green. So in your book there's a picture of 3 test tubes. 2 of them have changed green and 1 is still yellow. That would be an easy way to identify which one is the tertiary alcohol because there would be no oxidation. And that pretty much is the extent of what IB expects you to know about the alcohol homologous series.